Hello everyone, my name is Sofie Tilborghs and I will present you our work on shape-constrained CNN for cardiac MR segmentation with simultaneous prediction of shape and pose parameters. As you probably all know, CNNs are currently the state-of-the-art for many medical image segmentation tasks, including the segmentation of the myocardium in cardiac MR. But since conventional CNNs are predicting a probability for each pixel to belong to a structure, they lack explicit shape constraints, sometimes leading to unrealistic segmentations. Furthermore, if you want to calculate regional measures, you need to know the pose of the heart. To solve these issues, we propose to integrate a statistical shape model in a CNN. We do this by the regression of shape and pose parameters while simultaneously predicting a semantic segmentation. Our CNN is an encoder-decoder network composed of residual convolutional blocks with three outputs. One output for a number of parameters representing the myocardial shape, one output for the cardiac pose, and one output for semantic segmentation. The complete network is trained at once using a loss with contributions of each of the outputs. I will elaborate a little more on the different outputs and their associated losses in the next slides. The shape model is constructed starting from a point representation where both endo and epicardium are each represented by 18 landmarks. This representation is then normalized for pose using the center point of the left ventricle and the mid-septal orientation. After principal component analysis, each shape can be written as the mean shape plus a number of eigenmodes composed of a shape-specific coefficient, the magnitude of the eigenmode, and the eigenvector. The shape-specific coefficients B are the numbers we want to predict in our CNN. By using 12 eigenmodes, more than 99% of shape variation is represented. For both shape as pose, we used a mean squared error loss. For the semantic segmentation, we use a distance map representation where each pixel represents the Euclidean distance to a contour. The distance map is negative for pixels inside the structure and positive for pixels outside the structure. The loss is a weighted sum of categorical dice loss and mean squared error. To be able to calculate the dice loss, we binarize the distance map using a sigmoid conversion function. For training the CNN, we also used online data augmentation by addition of Gaussian noise and by adapting the shape and pose parameters. For the shape augmentation, a random number between -1 and 1 was added to the shape coefficients. The input images were then modified accordingly by using a template spline point-to-point registration between the original and augmented landmarks, while the distance maps were recreated using the augmented landmarks. In a first experiment, we performed an ablation study on a clinical dataset with 75 subjects suffering from a wide range of pathologies. The myocardium in short-axis images from apex to base in end diastole and end systole was manually delineated, resulting in a total of 1,539 delineated short-axis images. We performed a 5-fold cross-validation on 5 different setups. First, a conventional semantic segmentation using a dice loss. Second, a semantic segmentation using the combined dice and mean squared error loss on distance images. Third, a regression of shape and pose parameters. Fourth, combined regression and semantic segmentation. And finally, in the fifth setup, the online pose and shape data augmentation framework was introduced. In this slide, the results of the ablation study are shown. The top part of the table shows the metrics calculated from the distance map outputs, while the bottom part calculates the metrics from the regression outputs. As you can see, the combined distance and mean squared error loss was able to significantly improve the dice coefficients, the mean boundary error, and especially the Hausdorff distance. Adding the regression losses did not really help, but the pose and shape augmentation did. The bottom part of the table and the middle figure indicate that the regression on itself resulted in very bad predictions, but adding semantic segmentation significantly improved all metrics, except for the orientation error. And again, the shape and pose augmentation led to a final improvement. You should also note that while the joint semantic segmentation significantly improved the regression, the results remain significantly worse compared to the semantic segmentation outputs. In a second experiment, we used the predicted shape parameters to calculate LV area, myocardial area, 3 dimensions of LV, and 6 regional wall thicknesses, as was performed in the LV-Quan18 and the LV-Quan19 challenges. For this, we used the same clinical dataset as used for the ablation study, and additionally the LV-Quan18 and LV-Quan19 public datasets. In the table, the mean absolute error and the correlation between true and predicted values are given. On the right, 2 representative examples for each dataset are shown. For the one, we see again that both the addition of semantic segmentation as well as the data augmentation approach resulted in more accurate measurements. On the LV-Quan18 dataset, we compared our results with the results reported for the winner of the challenge and saw an improvement for LV area, myocardial area, and LV dimensions, while the results on regional wall thickness were slightly worse. For the LV-Quan19 challenge, we report the values of the first, second, and third places and compare with our results. For this dataset, we were not able to beat the results of the winner, which is likely due to the slight inconsistency that still exists between our distance map output and the regression outputs. To conclude, we presented a CNN approach to predict shape parameters that allow direct calculation of regional metrics. We saw that adding a semantic segmentation loss significantly improved the results, but also that the regression of shape parameters remains more difficult compared to semantic segmentation. In future work, we want to further investigate the possibility of an extra consistency loss between semantic segmentation and regression outputs. So, this was the end of my presentation. Thank you for listening, and if you want to have more details on this work, I invite you to read our paper. Feel also free to contact me if you have additional questions.